really are three separate limit ideas. They're all kind of small, just kind of making sure your foundation is solid. So the first part is calculator active, and it really involves two famous limits, but we're going to use a skill you need to know, which is how do you use your calculator to investigate limits, which you did way at the start, but you need to know that. So this is a really famous limit. The limit as x goes to 0 of sine of x over x. Now those of you in physics probably use this idea quite a bit. I think you've probably come to this, but has Mr. McKellips talked to you at any point where if x is small, then sine of x and x are relatively the same? Have you used that? Oh, AP physics students? Do I have any physics students in here? Okay, well then. That said, we're going to investigate it. This is a really famous limit. It's important in a lot of other aspects, including physics, but we'll talk about that. Now, if you want to investigate a limit, the first thing is, the structure is typically to put the thing you're trying to investigate in the middle. It's almost a visual or a graph imposed on a table. So if you are approaching 0, 0 needs to be approached from both sides. So that's why I put it in the middle. Now the idea is you approach it from both sides, and the proper way to approach is do it in an exponential, not linear, which is to say I don't take 1, then a half, and it's more like powers of 10. So 1 away, a tenth away, 100th away is the most common. Now that's above by 1, a tenth, and 100th. And then on the other side, we're also going to approach by 1, a tenth, and 100th, but on the negative side. So this would be negative 1. And then we'll get a little closer to 0, so negative 0.1. And then negative 0.0. Let's call this f of x, so we don't have to rewrite sine of x over x. Are you with me? All right, now, rather than write all that or type that in every time, sine of negative 1 over negative 1, sine of 0.1 over 0.1, let's put the function in so we can just call up f. And so would you, in a function, identify sine of x, oops, or w, sine of x, go outside the parentheses, divide by x, and call it good. And yeah, we could look at the graph, but the table is justification, so we're going to use a table, right? So name the function, and you can kind of see from the graph what it's going to look like, but the table is our justification. We don't usually, you don't use a graph as justification. You use analytical or numerical. So we want to start by getting closer and closer to 0 from the left. So would you call up the function and evaluate it at negative 1 and record 0.017? You follow me? Am I in degrees? I might be. Yes. All right, there you go. So you do it and get something better than I got. Sorry, this teaching pre-calculus is killing me. Oops. Okay. How about 0.841? Okay, cool. All right, so then you keep getting results. Somebody want to shout out their negative 0.1 result? 998 and 0.999. Okay. Are you getting the same results on the right-hand side? What does that seem to imply about the function? Continuous, that's not what I'm looking for. Try again. Symmetric about the y-axis, which means it's even. It's an even function. That actually is true. If you put negative x in, you get negative over negative, which is positive. It's basically double negative, making an even function. All right, so it seems like then our answer is that as we get closer and closer to 0, both one-sided limits are yielding the same answer. And that is sine of x over x approaches 1. That's kind of weird. You're really going to use L'Hopital's rule eventually. The idea is, yes, they both go to 0, but they go to 0 at the same rate. And the idea of using rates we'll get to later, but it is 1. All right, would you then do the same thing for the next? Putting in the function and completing a table to justify your work? Do you get the same results on both sides here? No, you get the same numerical value, but opposite sign. So they have the same absolute value, but not the same sign. So what does that imply about the function? 4, 0.004, 0.049, 0.459. Therefore, the limit appears to be
Yeah, we don't get negatives for the positives. Like,
oh, I think I put in 1 minus cosine. Darn it. We used the wrong function. Okay, thank you. So positives on the left and negatives on the right? Okay, thank you. That's it. The limit is still 0, whether it's 1 minus cosine or cosine minus 1. Sorry, different textbooks. Some call it 1 minus cosine and some call it cosine minus 1. It is the same either way. All right, cool. Thank you. The first part then is those two big limits. Now, if in the homework it just gives you the problem, then you surely may, if you recall, give the answer. But if it says to justify by table, then you need to make that table. Thank you. All right, so can you A, recognize those two important limits, and B, use a table to investigate limits? Can you do those? Yes. Give me a yes, I can do those. Yes. Okay, cool. The next idea is infiniteness, D and E, and such. There are actually 3 reasons a limit doesn't exist. Let's talk about lots of little problems here. If you took 3 over x, now I don't usually do these visually, but let's think graphically. Wouldn't you agree that 3 over x is just like 1 over x, and the 3 maybe stretches it a little, but it's still a vertical asymptote at 0? Do you agree? As you approach 0 from the right, you could express 2 different answers. What is one possible answer? Infinity, or you could say dne. Now, dne, because technically when you say what's the limit, you say what finite numerical value does y approach? And infinite is not a finite numerical value. So you are justified in saying there is no limit. There's no numerical value that's approached. It gets infinitely large. You with me? Mm-hmm. All right. Let's think about then, this kind of builds off what we did yesterday in that free response. Infinitely small, infinitely large. So think about this guy. This requires a little more thought. If you approach 0 here from the left side, this is e to the 0 from the left. And yes, it's 0 from the left, but let's think of this more like small negative, yeah? Are you with me? Okay. Now what about e to the 0, whether it be the left or the right? What is e to the 0? 1, okay? This then eventually simplifies down to 1 divided by a small negative. Let's deal with the sign first. Positive 1 divided by a negative is negative. And what happens if you divide 1 by a small number? And I'm talking 1 divided by 1 billion. Yeah, 1 divided by 1 billion is 1 billion. So it gets really large. Okay? So that would be negative. What about 3 over negative huge? So I know it's negative, but what happens when you divide a number by a huge number? It gets small. So this approaches 0. Yeah? And that actually makes sense. This one you do know the graph of. Wouldn't you say that as x goes to negative infinity, we're talking that behavior, and doesn't the graph or the y value approach 0 there? You follow? Okay. Try the last one in that row. See what you think. These are all different. You have to think of them each a little different. What do you think? Why 0? E to the x is massive. That's true. What about cosine, though? Does it even converge onto a single number? Okay, so how can I do this if I don't know what cosine approaches? Do you agree that cosine just bounces back and forth between negative 1 and 1? Yeah, think end behavior. This is strictly limited. Yes, it goes between negative 1 and 1, but those are pretty small numbers, and you're dividing by huge positive numbers. Now, doesn't that, regardless of what the cosine does, doesn't that have to approach 0? So yeah, end behavior says it all. Beautiful. Okay? All right. What about the limit as x goes to 0 of cosine? I'm not sure what I'm getting at there. That's pretty easy. What is that? Yeah, that's just direct substitution. I'm not sure what I'm thinking there. All right. What about the limit as x goes to infinity of cosine? D and E. Yeah, why? Yeah, it doesn't approach a single number. The definition of a limit is what single number does the y value approach. And this is D and E. Now write yourself a note here. Oscillation is another reason for D and E. So we've got 2 already in the books as far as D and E. D and E in the first case was the limit doesn't exist because it's infinite behavior. It doesn't approach a numerical value. So if it gets infinitely large, it's B. Although sometimes we say infinity. Oscillation, it fails to converge onto a single value. That also is a reason that sometimes D and E happens. And then what's the third D and E that I haven't touched on, but we have seen before? What's another reason the limit doesn't exist? Not continuous, kind of on the right track. Is this helping you here, what I'm doing here with my hands? Yeah, the one-sided limits aren't the same thing, yeah? That's also the limit doesn't exist. All right. What about this guy then? As x goes to 0 from above, what is 1 over x? Forget the cosine for a second. What does 1 over x approach? As x goes to 0 from above, then I'm getting small numbers. What's 1 over small positives? Infinity, yeah. Think cosine of infinity or cosine of big positives. Well, what is cosine of big positives? Just did this one. It does not exist, yeah? It fails to converge. Again, it's oscillation. All right. What about the last one? Try the last one. What do you think? 1. Why 1? Who said 1? Why did you say 1?
Because, so it's like 1, if you do the 1 over x, then that's like 1 over negative infinity.
Okay.
Which is like 1 over, there's like 0.
Uh-huh. Okay. Cosine of 1 over huge or negative huge is cosine of 0. Cosine of 0 is... That's very much the thought process. All right. This we've done to death for Pete's sake, but just, I don't know. What about the cosine, or no cosine, sorry. The limit as x goes to 0 from the negative of absolute value of x over x. What is it? 1 or negative 1? Negative 1. Do you agree the numbers would be the same, but the signs would be different? And so that is negative 1. All right. What about the next one then? What does the inside go to? And what does our cosine of 1 go to? That's at what angle is cosine 1? 0. Okay? You follow? And what about the last one? Doesn't exist. Justified. What is the limit as you approach 3 from below? 181. So imagine 2.9. Positive 1 or negative 1? It's actually positive 1, right? Because if you put 2.9 in, you would get same thing top and bottom. What about the limit as x approaches 3 from above? That's negative 1. If you try 3.1, for example, you get 0.1 in the top and negative 0.1 in the bottom. That's negative 1. Negative 1 is not equal to positive 1. That's why we're claiming unity. We cool? All right. The last one is more of an advanced limit technique. This is not done on the AP test very much, but it's definitely in college a lot. So it's called the sandwich theorem or the squeeze theorem. Depending on your book, it's called one of two things. And the name is very logical. All right. So let's talk a little bit about inequalities here. Inequalities. First thing I want you to understand is inequalities versus equalities. Now, inequalities, they're a little more gray area there, all right? Let's consider this, okay? Would you agree that this is true? Negative 2 is less than 1. Okay. Now, let's consider when you do a function to both sides, it's not like an equation where all of this stuff is true. Some of these things don't actually maintain truth. Now, here's what I mean. Say I added the same thing to both sides. Maybe added 1. Is truth maintained? Is that still true? Yeah, that stays true. Okay? Now, what if I multiply both sides by something? Is truth maintained? Not necessarily. What can I multiply by to make it false? Yeah, if you were to take a negative 1, then all of a sudden it becomes 2, and negative 1 isn't true even. No, that's why you were taught in Algebra 1 or sometime. When you multiply by negative, you have to switch the inequality to maintain truth. But if it's a positive, you don't have to switch the inequality. So the point is, inequalities are a bit of a mess for multiplying. What about squaring? If I square both sides, is truth maintained? No, now it's false, okay? So that's a bit of a gross thing. Now, the part I'm getting to is, what if I took the limit of both sides? Now, this isn't a function, really, but if I took the limit as whenever x approaches 0, that does maintain truth. And that's the part that you're going to use in the sandwich theorem, all right? So it goes a little something like this. I'll do the analytical part, then the visual here. Visual is how I understand it, but analytical is how you do it by the book. So imagine that you have 3 functions. So these are big graphs, okay? There's some graphs. And f is a function that's between g and h, or touching, but never above g, or never below g, and never above h. So f is somewhere squeezed in between it. Yeah? Are you with me? Okay. it is true then that if f is always between g and h, then if you look at what happens as you approach a certain value, then the y values or the limits have to be between g and h's limit. Now, a problem then might look like this. Say I gave you that f of x is some function between negative x squared and x squared, but I never tell you what f of x is. Could you, without knowing f of x, tell me what the limit of f is as x approaches 0? What is it? Okay, well, here we go. If this is true, then it is also true that the limit as x approaches 0 of each part is also true. You agree? Now, the reason I did that is because that's the question. What happens as x goes to 0 of this function? So I took the limit of all three things because they want the limit. I use 0 because that's what they wanted me to approach, yeah? Right? Do the left-hand limit. As x goes to 0, what does negative x squared approach? 0. What does the right side approach? 0. Now, we're saying then that the limit of f is between 0 and 0. It's getting squeezed, and therefore it must equal 0. If you were to think graphically, here, the graph helps a lot. Here's x squared. Here's negative x squared. Now, I don't know what f of x looks like. It could be anywhere in between. But what happens as you get closer and closer to 0, instead of having this huge gap between the two, we start to squeeze f, and it has to go in between the two. So the squeeze term and the sandwich term, it gets sandwiched, and it has to be 0. You follow me? Okay, try this one, please. Actually, try all three, and talk it over with your math amigos. In every case, you're taking the limit of all three components. Graph is good backup, but it's not justification, so do your proof analytically, please. How are we doing? Okay, so let's check your answers. For the second one, or the right hand one, did you get 0?
Yes.
Okay. Any questions about that one? Okay. Third one is a bit of a wacky question. I can do the limits okay, but it doesn't really get squeezed. I think you'll agree that graphically, you're talking about, yeah, they squeeze at 0, but at 3, there's no squeeze. F could be anywhere in here. So what did you say for the third one? Okay, so does not exist. I see what you're coming from, but does it mean that as x approaches 3, f, that it doesn't exist? There is no limit? Could it be a limit? Could there be a limit? No, it might exist. So you really should say something more like, not enough information. Okay, the limit might exist. You don't know that, but there isn't enough information to say. The squeeze term is not applicable. You follow me? And the last one? Excellent. Okay, if you got your homework from yesterday, please, I think you'll find, actually, yeah, that's right. There's a lot of really easy problems up tonight's one. Okay. The replacement problems answers, picking up after the free response that we did together and graded together. You see where I'm at, page 2? Okay, so 31 is 3. I'll be happy to go back over these. I'm just giving you answers. Okay, 3. Do we agree? All right, maybe not. For 32, when I sketch f, I'm saying where is the derivative positive, and therefore f is increasing. So I looked at this part to decide increasing, then I did this part to decide decreasing to 0, then increasing up to 2, but then increasing again after it goes flat. So something like that, yeah? When you do F double, you think totally differently. Instead, you say, where is it decreasing? And that means F double is negative. So you should have a negative up to a graph below the axis to -1, then above the axis where the function is increasing from -1 to 1, below from 1 to 2 because f is decreasing, f prime is decreasing, and then above the axis after 2 because f prime is increasing. All right? Really different thought processes. These guys, sorry I didn't give you a lot of room here. I should have given you more room here and less room there, but 15 is, or B, is the answer to that one, and -2 is the answer to 49. I should see a lot of work for 48, but not much work at all for 49. Okay? This, for A, u is x and dv is e to the 9x dx. For B, u is x, dv is secant squared x dx. And for C, u is log of 5x and dv is dx. B. All right? 2, 4x plus 7, that sum times e to the x minus 4e to the x plus c. 3 was u sub integration by parts or ultraviolet. If you said that, that's fine. U sub integration by parts, U sub integration by parts. Cool. 4 was -pi/2. It's a definite integral, so you should have a numerical answer. B is an indefinite integral, you're just finding an antiderivative. X over 4, e to the 4x, minus 1/16, e to the 4x plus c. We good? And whatever that one is, c, pi over 2 minus 1. And D. Depending on how you treated the second integral, you could have two possible answers. X over 2 tangent of 2x plus 1/4 log of cosine of 2x. Or instead of plus cosine, you could have negative secant, depending on how you approach it. All right. Let me know what questions you have. What? 21. What else? Is that a book problem?
Yeah.
Okay. 21 in the book. Nothing else on the extra practice? You killed it?
18.
Did you say 25?
Did you ask?
25, 18. Are those all book problems? Yeah. Okay. Okay. Alrighty then.
Really angry.
So I was thinking about this. Obviously this didn't occur to me the whole first semester. But teaching pre-calculus, I start to get a feel for where you guys are coming from. So in pre-calc, you graded your homework and you, if you missed them, you just said -5, right? Okay. That's not how you should be approaching this because you have all the answers to the problems. I think I told you this, but I posted all answers, all problems. Yeah? The even answers are on my website. You should miss no book problems. You should be, after doing your homework, checking your work and saying, oh, I missed 5, I missed 17. I feel like some of you are still in pre-calculus mode, like, I missed that one, I missed that one, I missed that one, and you're doing nothing about it. That's not good. You need to actually grade ahead of time and figure out, obviously, ones you have the answers for, and figure out, man, I either can figure out my mistake or I can't, and learn from your mistakes. Okay, just so we're clear. 21 on the book. Here we go, 21 on the book. Oh my goodness, I'm never going to get through this. Y equals 6x squared. Y equals 6 over x. X-axis, x equals k. K is greater than 1. Cool. Visual is not required, but surely is helpful. Here's 6 over x squared. Or 6x squared. Here's 6 over x. These guys meet. If you set these equal to each other, did you find that they meet at 1? Did you agree? Okay, cool. So when they say x equals k, which is a vertical line, and k is greater than 1, that implies that the k must be over here right at that intersection point. So we're talking in this problem this region. Kind of thing. Yeah? All right, so cool. Express the area as a function of k. Let's use x as the variable of integration. How many integrals will you need to get the area? Okay, draw rectangles. When I use x, I draw this way. Do I have the same upper and lower curves every time? I get a handoff of 2, so I need 2 integrals. The first is from 0 to 1, and it's under 6x squared, yeah? Down to 0. The next region is from 1 to where? K, and it's under 6 over x, yeah? All right, so if I were to integrate this, I wasn't sure if I was done yet or not, so I kept going. If I integrate this, this is 6x cubed over 3 from 0 to 1, and 6 log of absolute value of x from 1 to k. We? All right, so that's 2 times 1 minus 0 plus 6 log k minus 6 log 1. Do you agree? And therefore 2 plus 6 log k, because log of 1 is 0. That's part A. That's region, I guess they called it R, not A. But that's region R. You with me? All right. Now, obviously then, the area would depend on what k is. The bigger k is, the bigger R is. It's dependent on where you cut the interval up. So let's talk about the rest of the question. B, find the value of k that would make R equal to 20. Is that a little more doable now that part A is done? Yeah, so if you just set the r equal to 20 and solve. That should be easy enough if you have the pre-tab skills to solve that equation, which I know that you do. And then C is back to a calculus question. If the area of R is increasing at a constant rate of 8 square units per second, then doesn't that mean dr dt is positive 8 square units per second in calculus terms, right? They want at what rate k is increasing when k is 27. So we want, given that, you want dk dt when k is 27. So how do I get at dk dt given that I have an rk equation? Take the derivative with respect to time. So the derivative with respect to time of r is dr dt, 0 plus 6. What's the derivative of log k with respect to time? 1 over k, but chain rule, dk dt, right? I have to take the derivative of the variable as well, because I'm differentiating with respect to time. So plug in 8 and 27, solve for dk dt. You down? Okay. So the problem is I didn't get to 5. So, or 18. I'll tell you what I'll do. If you have questions on 25 and 18, I'll give you a pass. I will not mark them wrong, but I do want it by the end of the day. And if I have time, maybe I'll do that at the start of class. Okay? Have a good day. I need to go a little faster, obviously. Okay. Let's just have a nice day.